Hello my friends and welcome back to the You Can Do TV channel. Producing high-quality steel involves a series of carefully orchestrated processes, each contributing to the final product's superior properties. At ArcelorMittal Belgium, a fully integrated production site ensures an efficient and sustainable journey from raw materials to finished steel. Raw material preparation. The process begins with the arrival of iron ore and coal, essential raw materials for steelmaking. These materials are transported via waterways to optimize logistics. Iron ore undergoes sintering, where it is mixed with fluxes and recycled materials, then baked into a porous, solid material suitable for the blast furnace. Coal is converted into coke in a coking plant to serve as a reducing agent and fuel. Iron making. The blast furnace is charged with sinter, coke, and iron ore. Hot air injected at the bottom triggers a chemical reaction that reduces iron ore to molten iron. The carbon-rich hot metal is tapped into torpedo ladles, while byproducts like slag are processed for use in the cement industry. Additionally, blast furnace gases are partially converted to electricity or into value-added products through innovative technologies like carbon-to-value installations. Steel making. In the steel shop, molten iron is converted into steel. Scrap metal, which constitutes about 20% of the raw materials, is added to the converter. Oxygen is blown into the mixture to remove impurities, transforming the molten iron into liquid steel. This step reduces the carbon content and ensures precise chemical composition. Casting and rolling. Liquid steel is transferred to a continuous casting line, where it solidifies into slabs. These slabs are reheated and rolled in the hot strip mill to produce thin steel strips. For further refinement, the strips undergo cold rolling to achieve desired thickness and surface quality. Annealing restores ductility, while galvanizing applies a protective zinc coating, enhancing corrosion resistance. Coating and finishing. Steel can be further processed through electrolytic or hot dip galvanizing and organic coating lines, depending on customer requirements. These treatments provide additional protection and aesthetic finishes for applications in automotive, construction, and appliances. Sustainability initiatives. ArcelorMittal Belgium integrates renewable energy sources, such as solar and wind, into its operations. It also leverages cutting-edge technologies to recycle steel scrap and reduce emissions, maintaining one of the world's smallest carbon dioxide footprints in steel production. The production of shipping containers is a highly organized and precise operation, designed to meet international standards and ensure durability under extreme conditions. This meticulous process begins with raw materials and continues through multiple stages of fabrication, assembly, inspection, and final outfitting. Material preparation. The process starts with steel coils, which are transported to the cutting station. At this stage, the coils are unrolled and cut into sheets of predefined dimensions. These sheets are sorted, stacked, and placed into intermediate storage for further processing. Rust removal and priming of the sheets are performed in a fully automated sequence, ensuring the steel is free from impurities and ready for subsequent operations. Structural component fabrication. The production of a container's structural elements begins with shaping steel sheets into U-profiles, which form the base of the container. Additional components, such as corner posts and door locking bar fastenings, are also fabricated during this phase. The corner posts, which must withstand immense pressure, are rigorously tested to handle up to 97 tons of weight, simulating the stress from stacking 12 fully loaded containers. The sidewalls, made from 11 steel sheets welded into an 11.7 meter long panel, are another critical component. Welds must be flawless, as even minor defects can compromise the container's structural integrity. Similarly, top and bottom side rails are welded to connect the walls, understructure, and roof. Container assembly. Once the structural components are ready, assembly begins. The process involves connecting the sidewalls and corner posts, welding door frames and panels, and constructing the front wall. Precision and attention to detail are paramount, as any misalignment could lead to structural weakness. The understructure is then fabricated by welding bottom side rails to 37 crossmembers, creating a sturdy base. The sidewalls, front wall, and door elements are successively joined to the understructure. Finally, the roof panels are hoisted into place and welded, stabilizing the container's basic frame. Surface treatment and painting. The completed container frame undergoes a second round of shot blasting to smooth the surface and prepare it for painting. Fine iron particles are used to ensure an even finish. The container is primed in a paint booth, followed by a final coating application. Each layer is carefully inspected, with coating thickness measured in micrometers to meet standards. After painting, the containers are dried in a heated chamber to ensure durability. Flooring production and installation. The flooring process takes place in a dedicated facility, where various wood types, beech, birch, pine, eucalyptus, bamboo, and tropical hardwoods, are prepared. Wooden panels are bonded with specialized glue and pressed together in cold and hot presses. The cold press applies a force of 16 tons for 20 minutes, while the hot press bakes the layers at 135 degrees Celsius for 75 minutes. The finished boards are trimmed to precise dimensions and undergo quality inspections before installation. In the container, floorboards are drilled and fastened to the crossmembers with screws, completing the base. Sealing the floor protects it from moisture and ensures long-term durability. Final assembly and quality assurance. The final production stages include attaching accessories, logos, and information plates. Stencils guide the placement of company logos, while weight and capacity information is affixed to ensure compliance with international shipping regulations. Door seals, locking bars, and handles are installed to provide protection against water ingress and corrosion. Forced ventilation systems are integrated to allow airflow while preventing water entry. Every container undergoes a series of rigorous inspections. This includes splash water tests and prototype load tests conducted at regular intervals. These tests verify water resistance and structural integrity, ensuring the container meets ISO standards. Only after passing these evaluations does a container receive a CSC, Container Safety Convention, plate, certifying it for use in shipping. The steel drum production industry plays a critical role in the global packaging sector. Steel drums, commonly referred to as industrial drums, are used primarily for the storage and transportation of bulk liquids, chemicals, food products, and hazardous materials. The production of steel drums involves several critical processes. Steel coil selection. High-quality steel coils, typically made from cold-rolled or hot-rolled steel, are selected based on their thickness and strength characteristics. The most common steel thickness for drums is around 0.8 to 1.2 millimeters. Forming and shaping. The steel coils are unrolled and passed through machines that cut, shape, and form the metal into the cylindrical body of the drum. With their durability, strength, and ability to be recycled, steel drums are favored in industries requiring robust, secure packaging solutions. In 2023, the global market for steel drums was valued at approximately $5.8 billion and is expected to grow at a compound annual growth rate of 4.1% from 2024 to 2030. End closure and sealing. The drum is closed at both ends, often with a flange design. These ends are then welded or sealed to ensure the drum is leak-proof, especially when storing hazardous liquids. Coating and finishing. After shaping and assembly, steel drums are coated with protective materials to prevent rust and corrosion. Technological advances in drum manufacturing. The steel drum production process has evolved over time with significant advancements in automation and robotics. Modern drum manufacturing plants are highly automated, with advanced welding machines, robotic arms for assembling parts, and automated coating lines that ensure the drums meet high standards for quality and performance. These technological innovations have led to reduced labor costs, improved efficiency, and enhanced product quality. One major technological development is the introduction of the two-piece drum design, which eliminates the need for welding seams on the sides of the drum. This design is particularly useful in ensuring that the drums are leak-proof and structurally stronger. The automated processes also enable manufacturers to customize steel drums for specific applications, such as adding internal linings to prevent corrosion or making modifications to the drum's ends to accommodate specialized closure mechanisms. Additionally, innovations in steel drum recycling have significantly improved sustainability. Steel is one of the most recyclable materials, and steel drums can be reused or repurposed many times over. In fact, over 90% of steel drums are recycled, reducing the need for new raw materials and minimizing environmental impact. Environmental impact and sustainability. Sustainability is a major focus in the steel drum production industry, as concerns over environmental impact and waste reduction become more prominent. The recycling rates for steel drums are among the highest in the packaging industry, with steel drums being reused in a variety of ways, from repurposed containers for storage to being remanufactured into new drums. The steel drum industry has also responded to the increasing demand for environmentally friendly solutions. This is typically done through processes such as powder coating or painting. The drums may be further lined with a protective layer, depending on the intended use. Market demand and applications. The steel drum market's demand is closely tied to global trade and the movement of bulk goods. The primary industries driving demand for steel drums include chemicals, food and beverages, pharmaceuticals, and petroleum. Steel drums are commonly used in the transport of chemicals such as solvents, oils, acids, and various industrial liquids. In the food and beverage sector, steel drums are employed for packaging liquids like oils, syrups, and even non-alcoholic beverages. In 2023, approximately 10 million metric tons of steel drums were produced globally. The chemical industry is the largest consumer of steel drums, accounting for over 50% of the total demand. The oil and gas industry also uses steel drums extensively for storing lubricants, fuel, and other petroleum products. The food and beverage sector is a growing market, particularly in regions where bulk food products are exported. For example, in North America alone, around 1.5 million steel drums were used annually in the food and beverage industry. The square steel can production industry is a key segment in the manufacturing sector, focused on the creation of steel cans in square or rectangular shapes. These cans are typically used for packaging food, beverages, and industrial products. The production process involves several key steps: steel coil preparation, cutting, shaping, welding, and forming. The finished cans are then subjected to a series of quality control tests to ensure they meet industry standards. In 2024, the global square steel can market is valued at approximately $10 billion, with steady growth expected due to the increasing demand for durable, eco-friendly packaging. The production capacity of leading manufacturers in the industry is impressive, with some plants producing over 200 million square steel cans annually. The automation of the manufacturing process has increased efficiency, reducing production times by up to 40%. China and the United States dominate the production of square steel cans, with China contributing to nearly 35% of the global output. The US follows closely, contributing about 25% of total production. Additionally, countries in Europe, such as Germany and Italy, also play a significant role in the market. Hyundai Steel's Dangjin facility in South Korea is a leading producer of high-carbon and alloy steel large bars, primarily for automotive applications. Starting materials and initial processing. The process begins with starting blooms measuring 390 by 530 millimeters in cross-section and lengths ranging from 3.5 to 8 meters. These blooms are subjected to both hot and cold charging, depending on production requirements. An integrated weighing system ensures precise material tracking. The blooms then proceed to a reheating furnace with a capacity of 200 tons per hour, where they are heated uniformly. A high-pressure water primary descaler removes scale buildup from the surface. Breakdown mill stage. The breakdown mill consists of a 47-inch, two-high reversing housing type mill with a maximum roll diameter of 1,200 mm and a barrel length of 2,600 mm. The pass count at this stage is carefully controlled to ensure dimensional accuracy. Continuous finishing and sizing mill. A high-pressure water secondary descaler removes any remaining scale before the bars enter the 6-stand continuous finishing and sizing mill. The finishing stands use Red Ring Series 5 technology, with a maximum working roll centerline distance of 1,030 mm and a barrel length of 1,200 mm. The sizing stands, employing CGA technology, have an 870 mm maximum working roll centerline distance and a barrel length of 1,200 mm. Both stands feature a quick stand change system to minimize downtime. Cutting, marking, and cooling. Cut-off operations are performed using two metallic disc saws with nominal diameters of 1,800 mm. These saws handle head cropping and commercial length dividing. Round bar manufacturing process. After initial reheating and descaling, the bars proceed through a continuous mill with ProScan laser profile gauges for precise dimension monitoring. Flying dividing shears with a cutting capacity of 300 tons perform initial cuts, followed by additional processing at the exit roller table. Cut-off machines, equipped with 1,800 mm nominal diameter metallic discs, handle head cropping and commercial length dividing. The bars are then marked at a bar end marking station. Controlled cooling is performed using specially designed cooling beds, where the bars are rotated continuously to ensure uniform cooling and prevent deformation. The aluminium extrusion process transforms aluminium billets into intricate profiles through a series of steps. It begins with loading the extrusion line, where logs of aluminium alloy are placed into the system. These logs are preheated to an optimal temperature in a heating furnace to ensure malleability. Once heated, the log is transferred to a shear mechanism where it is sheared into billets of appropriate length for the extrusion press. The billet is then fed into the press, where a hydraulic ram forces it through a die with the desired profile shape. This step, known as extruding, is the core of the process. If the production involves multiple profiles, changing the die ensures flexibility in meeting varied design requirements. As the aluminium emerges from the die, the profile is extruded continuously and is often cut on the fly into manageable lengths by a flying saw. These lengths are then moved to a stretching station, where they are straightened and stress relieved to achieve dimensional accuracy and strength. The stretched profiles are grouped in batches and transferred to a saw for precision cutting to required lengths in the batching and sawing stage. After sawing, the profiles proceed to automatic stacking, where they are systematically arranged for further processing. Managing the skips involves organizing the extruded profiles in skips or trolleys for efficient handling and transportation within the plant. Finally, the profiles are subjected to aging, a heat treatment process that enhances their mechanical properties by strengthening the alloy. The production of high-quality printing plates begins with the transformation of raw bauxite ore into a durable aluminum substrate. This intricate process spans several stages to ensure the creation of a stable, high-performance base for offset printing. From bauxite to aluminum. Bauxite, primarily mined near the equator, is the primary raw material. The ore undergoes refining to remove impurities, resulting in a white powder called alumina, aluminum oxide. Typically, 2 tons of bauxite yield 1 ton of alumina. The alumina is transported to smelting facilities, where it is subjected to electrolysis at around 700 degrees Celsius. This process produces molten aluminum, which is then cast into massive ingots, each measuring up to 9 meters and weighing over 30 tons. These ingots serve as the foundation for further processing. Rolling and shaping. The aluminum ingots are preheated to 500 degrees Celsius for hot rolling, ensuring uniform internal and external temperatures. This step reduces their thickness and prepares them for cold rolling. In the hot rolling phase, the ingots are flattened to about 4 millimeters thick and wound into coils stretching over 2.4 kilometers. After cooling, these coils are transported to the cold rolling section, where the aluminum is further reduced to the required thickness, typically between 0.15 and 0.3 millimeters for printing plates. Coating and plate manufacturing. The coils are shipped to specialized coating plants, such as Agfa Graphics facility in Wiesbaden, Germany. Here, the aluminum is transformed into high-tech printing plates through a continuous production process spanning over 200 meters. The aluminum is first unwound and cleaned through an etching process. It is then roughened using electrochemical graining to enhance its lithographic properties. In the coating phase, a photosensitive or thermal-sensitive layer is applied to the aluminum. This coating will later form the printable image or text. Rigorous quality control, including laser and visual inspections, ensures the integrity of each plate. The coated aluminum is cut to size, covered with protective sheets, and packed in recyclable, light-tight boxes for shipment. Milk tanks are essential equipment in dairy farms, designed to rapidly cool and store fresh milk while maintaining its quality. The production process begins with stainless steel sheets, which form the inner tank. High-precision laser welding machines create specialized template evaporator panels, where refrigerant will flow for efficient cooling. These panels are meticulously shaped, welded, and inspected to ensure maximum durability and cleanliness. Once the inner tank is prepared, template panels are inflated to a specific height, optimizing cooling performance. Insulation is applied using a unique method that minimizes contact between the inner and outer tanks, reducing energy consumption. Throughout production, rigorous quality checks are conducted to maintain high standards. After the outer shell is formed, essential components such as legs, milk outlets, agitators, sensors, and control units are installed. For larger silo tanks, additional cladding and alcoves are added. The tank undergoes a thorough cleaning process before the final quality tests are performed. The non-stick pan production industry is a thriving sector, driven by demand for convenient, low-maintenance cookware. A standard production process involves aluminum sheet pressing, shaping, and precision coating, followed by curing at 400 degrees Fahrenheit to 500 degrees Fahrenheit to bond the non-stick surface. High-end manufacturers utilize advanced plasma spraying and multi-layer coatings for enhanced durability. Daily production rates vary widely, with large-scale factories producing over 10,000 pans per day. The industry faces challenges in sustainability, as traditional PTFE coatings release harmful substances during production. Consequently, many manufacturers are shifting toward eco-friendly ceramics, which are free of per- and polyfluoroalkyl substances. With a focus on innovation and regulatory compliance, the sector continues to cater to a global market seeking durable, safe, and versatile cookware. Globally, the market for non-stick cookware was valued at $9.7 billion in 2023 and is projected to grow at a compound annual growth rate of 5.5% from 2024 to 2030. The upcast process is an ideal solution for producing high-quality copper rods and tubes from recycled copper scrap. By incorporating advanced equipment like the lift tipper and turnable storage feeders, this system ensures efficient, reliable, and cost-effective operations in recycling industries. When using recycled copper scrap as the raw material, it is essential to first ensure the material is as pure as possible. Recycled copper typically requires a longer dwell time in the melting furnace to remove impurities. Therefore, it is recommended to use a separate melting furnace for copper scrap to avoid contamination with cathodes and ensure high-quality output. This step is crucial in producing oxygen-free Cu of copper rod, which is commonly used for electrical applications and other precision industries. The system itself consists of a furnace and casting machine, designed to meet various production needs. For higher output, a double or triple furnace setup is used. The double furnace configuration features separate melting and casting furnaces, while the triple furnace arrangement is best for handling both copper cathodes and recycled copper simultaneously, maximizing material use. The furnaces are electrically heated and equipped with channel inductors for efficient energy use and precise temperature control. Once the recycled copper scrap is melted, it is fed into the casting machine. The casting machines are multi-strand systems, capable of casting different rod and tube sizes at the same time. The coolers are individually designed for each strand, ensuring uniform cooling as the products are pulled upwards by a servomotor-driven withdrawal system. The cooled rods or tubes are then guided to coilers, where they are wound into compact coils for easy handling and transport. To optimize material handling during the process, the lift tipper is integrated into the system. This robust and efficient piece of equipment is designed to lift and tip the copper scrap into the furnace, offering precise discharge control and minimizing downtime. Additionally, the turnable storage feeder ensures the smooth and controlled dosing of materials, with variable feed rates that can be adjusted to match the specific requirements of the casting process. China is the world's largest producer of cookware, accounting for over 60% of the global output. The industry encompasses a wide range of products, including pots, pans, woks, and pressure cookers, catering to both domestic and international markets. In 2024, China's cookware industry generated an estimated revenue of $30 billion, with exports contributing around $18 billion. Key export destinations include the United States, Europe, and Southeast Asia. The production hubs are concentrated in Zhejiang, Guangdong, and Jiangsu provinces, with Zhejiang's Yangkang City often referred to as the hardware capital of China. It hosts over 1,000 cookware manufacturers, contributing significantly to China's annual production capacity of approximately 2 billion units. Technological advancements have driven innovation in the sector. Over 70% of manufacturers have adopted automated production lines, incorporating technologies such as laser cutting and robotic polishing to enhance efficiency and quality. Environmental regulations have also prompted the use of eco-friendly coatings, such as ceramic and water-based non-stick materials, replacing traditional PTFE coatings. The domestic market is experiencing a growing demand for premium cookware, spurred by urbanization and rising disposable incomes. With exports growing at an annual rate of 6%, China remains the global leader in cookware production, meeting the needs of both budget-conscious and high-end consumers worldwide. Metal spinning is an advanced metalworking technique widely utilized in various industries to create rotationally symmetrical components with precision and cost efficiency. This process involves pressing a circular metal disc onto a rotating mold using a steel roller, shaping the metal into the desired form. The mold is typically crafted from untempered steel, though tempered tools are preferred for enhanced surface quality and durability, especially when working with stainless steel. For prototyping or small-scale production, even wooden molds can be used. Modern metal spinning leverages CNC machinery for high speed, accuracy, and consistency. However, hydraulic and manually operated machines remain in use for simpler parts, models, or limited production runs. The versatility of metal spinning allows the production of a wide range of sizes and forms, making it suitable for items like inlet cones, domes, and various other components. The process begins with cutting metal sheets into circular blanks using NC circular shears or similar equipment. The metal is then formed against the mold, either manually or automatically, depending on the machinery employed. Additional techniques like deep drawing, bending, and punching often complement metal spinning to achieve complex designs. Key advantages of metal spinning include low tooling costs, easy setup, and adaptability to diverse materials, such as 2 mm zinc-coated steel. Its proficiency in producing both prototypes and high-volume parts ensures its continued relevance in the modern metal industry.